Tonight, we begin a quiet journey, a slow drift across the immense canvas of the cosmos to explore a question that has, for countless centuries, lingered at the very edge of human thought. What truly lies beyond the furthest reaches of everything we can possibly perceive? We're not just talking about distant stars or galaxies here, but the ultimate, profound mystery of what exists beyond the universe itself as we understand it. It's a concept that stretches the very fabric of our imagination, inviting us to contemplate scales of space and time that nearly defy comprehension. So, before you get comfortable, take a moment to like the video and subscribe. Let me know in the comments where you are in the world and what time it is for you. Our universe, this vast, shimmering tapestry of celestial wonders, has always presented itself as the ultimate frontier. It's a realm seemingly without end, a boundless expanse pregnant with infinite possibilities and countless enigmas that have, quite literally, puzzled humanity since the dawn of conscious thought. For eons, we have gazed up at the night sky, a sparkling dome overhead, and pondered the silent, ancient mysteries held within its depths. From the colossal, echoing voids that punctuate the cosmic foam, those truly immense stretches of apparent nothingness between galactic superclusters, to the almost inconceivable very beginning of time itself, a moment so singular and profound it birthed all existence, we are constantly drawn into a deep, introspective journey. Tonight, we embark on such a journey, a slow, deliberate exploration into the profound enigmas that define our universe, and will gently ponder its ultimate, distant future. We will, in our minds, travel back through the eons, to the earliest whispers of existence, to the very dawn of the universe, that momentous point when everything we know sprang into being. We'll then trace its grand, sweeping evolution through billions of years, witnessing the formation of the first stars, the swirling birth of galaxies, and the intricate dance of cosmic structures. And from there, we will gaze forward, far into the unimaginably distant future, attempting to envision the ultimate fate of this incredible, ever-changing cosmos. As we drift along this temporal current, our minds will inevitably seek out the boundaries of the cosmos, an inherent human drive to define and delineate. We'll find ourselves asking, with genuine curiosity and a touch of awe, if there truly is an edge, a final, definitive limit to all that we know, to all that we can observe, and indeed, to all that is. In the truly vast, almost overwhelming expanse of the universe, there resides a deep, pervasive mystery, one that continues to elude our complete understanding. It's a mystery that relentlessly stirs our collective imagination, igniting sparks of wonder within us and simultaneously challenging the very foundations of our current scientific and philosophical understanding. At its heart, this profound mystery is encapsulated in a single, compelling question: what, precisely, lies beyond the universe as we currently perceive and comprehend it? As we mentally journey through the intricate, interwoven tapestry of space and time, we are inevitably confronted with a humbling, yet equally profound, realization. Our vision, our ability to directly perceive the true extent of the cosmos, is inherently limited. We find ourselves, in a very real sense, imprisoned within the confines of what is known as our observable universe. This isn't a physical prison, of course, but a boundary dictated by the speed of light and the finite age of the universe. What then, truly, lies beyond these very real, yet somewhat arbitrary, observational boundaries? That, my friends, remains the deepest, most enduring of mysteries. It's like a cosmic curtain, draped across the furthest reaches of our perception, shrouding and enveloping the most fundamental secrets of existence itself. The very concept of beyond, in this context, quickly transcends mere spatial distance and evolves into a complex philosophical problem. How can we, as beings confined to a specific point in space-time, possibly begin to comprehend a realm that, by its very definition, lies utterly beyond our current perception, beyond the reach of our most sophisticated instruments, and perhaps even beyond the limits of our theoretical frameworks. This is a challenge that pushes the absolute boundaries of human thought, stretching our cognitive capacities while simultaneously sparking an insatiable curiosity within us, an innate drive that encourages us to tirelessly seek out answers, even when those answers seem to recede further with every step we take. Let's gently clarify what we mean by this observable universe. Simply put, it encompasses everything we can, in principle, see or detect from our vantage point here on Earth. This includes everything from the immediate surroundings within the room you might be in right now, to the most incredibly distant galaxies. Those faint, ancient smudges of light that can only be glimpsed and analyzed through the immense, light-gathering power of our largest, most sophisticated telescopes. Anything that can reflect light, emit light, or in any way direct light or other detectable radiation towards us, enabling our instruments to capture it, falls within this observable sphere. It's important to remember that this is not the entire universe, but merely the portion from which light has had enough time to reach us since the Big Bang. Currently, the widely accepted radius of this visible universe, stretching out in all directions from us, is approximately 46.5 billion light-years. Now, this number often sparks a moment of quiet contemplation, a gentle furrowing of the brow, because the age of the universe itself is estimated to be only about 13.8 billion years. This apparent discrepancy, where the radius of what we can see is significantly larger than the age of the universe multiplied by the speed of light, seems, at first glance, to be a cosmic paradox. However, this fascinating puzzle has a very elegant, albeit initially counterintuitive, explanation. It all comes down to one of the most fundamental and profound aspects of our cosmos, the expansion of the universe. Imagine, if you will, the very fabric of space itself, not as a static, unchanging backdrop, but as a dynamic, stretching entity. Since the cataclysmic event of the Big Bang, space has been continuously expanding, carrying galaxies and all other cosmic structures along with it. This isn't like galaxies moving ours through space, but rather space between galaxies stretching and growing. So, when we observe light from a galaxy that is, for instance, 13 billion light-years away, that light has indeed traveled for 13 billion years. But during those 13 billion years, the space between that galaxy and us has also expanded considerably. The original point in space where that light was emitted and the galaxy itself have moved much, much further away from us. Therefore, the light we are receiving now, from an object that emitted it 13 billion years ago, has traversed an ever-expanding path. By the time that ancient light finally reaches our telescopes, the galaxy that originally emitted it is no longer 13 billion light-years away from us in current cosmic distance, but has been carried much further by the relentless expansion of space. It's like sending a message across a rapidly inflating balloon. By the time the message reaches the other side, the distance between the sender and receiver has increased dramatically. This is why the objects whose light left them 13.8 billion years ago are now, in fact, 46.5 billion light-years away from us. These 46.5 billion light-years represent the effective boundary of our observable universe, a sphere centered on us, from which light has had sufficient time to reach us, accounting for the continuous stretching of space during its journey. It's a boundary defined by light itself, a cosmic horizon of visibility. Even if the entire universe beyond this observable sphere is truly infinite, stretching on endlessly into an unimaginable cosmic expanse, modern cosmology, at this present moment, simply doesn't possess the tools or the means to definitively know what may lie beyond this observed boundary. These cosmological limits, often referred to as horizons, are fundamentally dictated by the nature of light and its finite speed, and by the age and expansion of the universe. Consider, for a moment, the simple act of looking up at the night sky. We don't see it completely filled, wall to wall, with the blinding brilliance of countless stars, even though the universe is teeming with them. This isn't because there aren't stars in every direction, but precisely because of the inherent limits set by light. Light has a certain maximum distance from which it can reach observers here on Earth within the lifespan of the universe. It's as if there's an immense, spherical barrier around us, an invisible membrane, beyond which lie billions upon billions of other distant stars and galaxies, whose light simply hasn't had enough time to travel across the vast, expanding cosmic distances and reach our eyes or our instruments. This concept gives rise to several crucial types of horizons. The first is called the particle horizon. The particle horizon essentially defines the maximum distance from which light, emitted at any point in the past, has had the opportunity to reach us now. It marks the boundary of the region of space that we could, in principle, have observed up to this present moment. Imagine a light signal sent out from the very earliest moments of the universe. The particle horizon is the current distance to that point from which the light is just now arriving. However, there's another, subtly different concept known as the event horizon. While the particle horizon looks backward in time, defining what we have seen, the event horizon looks forward. It represents the maximum distance from which light emitted now will ever be able to reach an observer in the future, given the continued expansion of the universe. If a galaxy is beyond our event horizon today, any light it emits from this moment forward will never reach us, no matter how long we wait, because the space between us and that galaxy is expanding faster than the light can travel. But beyond these two horizons, there lies yet another limit, one that speaks to the very speed at which galaxies are receding from us due to the expansion of space. This is known as the Hubble horizon. If space objects, such as galaxies, are located beyond this particular boundary, it becomes, for all practical purposes, impossible for us to ever see them, even if we were to wait for billions upon billions of years. This is because these objects are constantly moving away from us, carried by the expansion of space, at a speed that effectively exceeds the speed of light relative to our local frame. It's a crucial distinction. Objects aren't moving through space faster than light, but the space itself, between us and them, is expanding at such a rapid rate that their effective recession velocity appears superluminal. Because of this profound effect, it appears to us, from our limited perspective, that the universe itself is somehow bounded or limited, when in fact, it is simply the finite speed of light and the accelerating expansion of space that impose these observational constraints upon us. You are, of course, well aware that the light traveling to us from bright cosmic objects does not, by any means, traverse the vast emptiness of space at an infinite speed. It travels at a fixed, immutable velocity, the speed of light, approximately 299,792, 458 meters per second in a vacuum. This fundamental constant of nature has profound implications for how we perceive the universe. For instance, our own star, the Sun, is situated at an average distance of about 94 million miles, or roughly 150 million kilometers, from our planet Earth. At the speed of light, it takes approximately 8 minutes and 20 seconds for the light generated on the Sun's surface to make its incredible journey across the interplanetary void, and finally reach our eyes. This means that when you look at the Sun, you are not seeing it as it is right now, but as it was 8 minutes and 20 seconds ago. Let's consider another example, a star far more distant. Proxima Centauri, the closest star to our solar system, is located at a distance of about 4.2 light years away from Earth. A light year, as you know, is the distance light travels in 1 Earth year. Therefore, the light from Proxima Centauri takes approximately 4.2 Earth years to reach us. When we observe Proxima Centauri through a telescope, we are seeing the star not as it appears in its current state, but rather as it looked 4.2 years in the past. This temporal delay is a universal constant when observing the cosmos. So, it elegantly turns out that we can only ever truly see events that happened a certain amount of time ago, in the past. Every glimpse we take into the depths of space is, in essence, a profound journey back in time. Yes, we can say, with absolute certainty, that we are literally looking back in time when we cast our gaze up to the star-dusted sky at night. The further we look, the further back in time we are peering. To truly update our knowledge about some extremely distant object, such as the HD1 galaxy, which currently holds the record for one of the most distant known galaxies, situated an astonishing 13.4 billion light-years away, we would need to wait an equivalent amount of time, 13.4 billion years, for any new light emitted today from that galaxy to finally reach us. This is, of course, a timescale that utterly dwarfs human existence, making direct real-time observation impossible. And this is all provided, of course, that there are no cosmic obstacles, like intervening black holes or dense nebulae, positioned in the immense pathway of that light, which could either absorb or distort its journey. If we could, hypothetically, examine this galaxy in exquisite detail, studying its structure, its stars, and its composition, we would be gleaning invaluable insights into how our own galaxy, the Milky Way, might have formed and evolved during the very early stages of the universe. It would be like looking at a primordial blueprint, a cosmic infancy. Therefore, the detection and meticulous analysis of light from these ancient, distant sources is of paramount importance for scientists engaged in the study of the evolution of the universe. It is thanks to this remarkable ability to peer into the cosmic past through the light of distant galaxies that we have been able to develop and refine our most widely accepted cosmological model, the Big Bang Theory. This theory describes the universe as having originated from an extremely hot, dense state, and then expanding and cooling over billions of years to form the cosmos we observe today. The monumental consequences of the Big Bang, such an energetic and transformative event, could not but leave an indelible trace, an echo resonating through the fabric of space-time. And indeed, such a trace was serendipitously found by researchers in the mid-20th century, individuals who were deeply immersed in studying various theories concerning the origin of the universe. In the year 1964, 2 American radio astronomers, Arno Penzias and Robert Wilson, while working with a large horn antenna at Bell Labs in Holmdel, New Jersey, picked up a strange, persistent signal with their incredibly sensitive radio telescopes. This signal was peculiar because it seemed to be coming from every direction in the sky, with precisely the same intensity, a faint, uniform hiss that they initially attributed to pigeon droppings inside their antenna. After meticulously cleaning their instrument and ruling out all terrestrial interference, they realized they had stumbled upon something truly extraordinary, something that had been predicted by Big Bang theorists years earlier. It turned out to be a remnant, a fossilized echo, of the very first light that appeared in the universe, the cosmic microwave background radiation, or CMB. This ancient light offers us a direct, unfiltered glimpse into the universe when it was a mere infant, only about 380,000 years old. In the earliest stages of the Big Bang, during what's known as the recombination era, the universe was incredibly hot and dense, a searing plasma of fundamental particles. The extreme temperatures meant that atoms, as we know them, could not yet form. Electrons and protons, the basic constituents of hydrogen, could not combine and settle into stable configurations. The radiation of photons, those fundamental particles of light, were constantly scattered off free electrons or absorbed by them, much like light trying to penetrate a very thick fog. Consequently, light simply could not travel far before being deflected or absorbed. The universe was then, quite literally, as opaque as a dense, omnipresent fog, completely impenetrable to light. However, after approximately 380,000 years following the Big Bang, as the universe continued its rapid expansion, everything began to cool down significantly. The temperature dropped to a critical point, allowing the first stable, neutral atoms of hydrogen and helium to finally appear. At this precise moment, the electrons could combine with protons and atomic nuclei, effectively clearing the cosmic fog. The universe became transparent, and light, for the very first time, was able to spread freely, unimpeded, over truly vast distances. This momentous event, often called last scattering, released a flood of photons that have been traveling through space ever since. And it is this very light, this ancient, stretched-out radiation, with its current faint temperature just above absolute zero, approximately 454 degrees Fahrenheit or 2.7 Kelvin, that we now record as microwave radiation. We can detect this faint glow in every direction from Earth, appearing to originate from a spherical shell at a distance of about 13.8 billion light-years. It is precisely because of this specific distance, corresponding to the time when this light was emitted, that scientists initially assumed the age of the universe to be the same number of years. However, as you already know, this may be only the limit of our vision, the edge of what we can currently perceive, rather than the absolute edge of existence itself. Nevertheless, the CMB cannot be seen by human eyes directly. The intensity of this first light, having traveled for billions of years and stretched by the expansion of space, is far too low to be perceived by our biological sensors. This extremely low intensity is primarily due to the ongoing expansion of the universe, a phenomenon we'll delve into in more detail a little later. This expansion causes the light waves themselves to stretch out, much like ripples on a pond expanding outwards. As these light waves stretch, their wavelength increases, shifting them from the visible spectrum into the microwave part of the electromagnetic spectrum, and they simultaneously lose energy, becoming fainter and fainter. So, they are barely visible, detectable only by highly sensitive microwave instruments. Despite its incredibly low power and elusive nature, the cosmic microwave background radiation acts as an extraordinary window, allowing us to peer through a crack in time, right back to the very beginning of the universe as we know it. The entire, nascent image of the universe's past, its infant stages, is revealed to scientists through the intricate patterns within the CMB. It is thanks to the meticulous study of the CMB that we now possess a comprehensive understanding of the Big Bang scenario, charting how our world, our entire cosmos, developed from an incredibly hot, dense singularity to the vast, complex, and still evolving universe we observe at this very moment. Thus, the map of the sky, when rendered in terms of the temperature fluctuations of this relic radiation, presents itself as a beautifully intricate, spotted pattern. In this cosmic fingerprint, blue areas typically represent regions that were slightly below the average temperature of the early universe, while the orange and red areas indicate regions that were slightly above it. These subtle temperature variations, incredibly minute yet profoundly significant, are not random. They are, in fact, the primordial seeds of all structure in the universe. Scientists study these spots with immense care as they allow us to trace the evolution of stars and galaxies. These density changes, often referred to as the seeds of structure formation, eventually coalesced under gravity over billions of years, giving rise to the clusters of galaxies and the vast cosmic voids we see today. The hot and cold spots of the CMB are, in essence, the initial irregularities from which all cosmic architecture sprang. In addition to revealing the origins of cosmic structure, the largest spots observed in the CMB, those covering approximately 1 angular degree in the sky, have become one of the most compelling proofs supporting the flat model of the universe. A flat universe, in cosmological terms, refers to its overall geometry. If the universe were positively curved like the surface of a sphere, or negatively curved like a saddle, the angular size of these spots would appear different. The observed size perfectly matches the predictions for a flat geometry, implying that on the largest scales, space is essentially Euclidean. Conversely, the smaller spots within the CMB map have revealed an absolute wealth of data concerning the precise composition and the precise age of the cosmos. By analyzing the statistical distribution and characteristics of these smaller fluctuations, cosmologists can infer the relative proportions of different components in the universe. Thus, the meticulous study of the temperature features within the CMB has become another powerful and independent proof of the existence of both dark matter and dark energy, two of the most mysterious and dominant components of our universe. Indeed, as far back as 2003, a group of astute astronomers, led by the distinguished D.N. Spergel, made a groundbreaking discovery. Their analysis of the CMB data revealed that the combined amount of dark matter and dark energy significantly exceeds the amount of ordinary, visible matter by several factors. According to the very latest, most precise measurements available to us today, the universe's energy density budget is distributed roughly as follows. Dark matter constitutes approximately 26.8% of the total mass energy, while dark energy accounts for an even larger share, a staggering 68.3%. This leaves ordinary, baryonic matter, the stuff that makes up stars, planets, and ourselves, as a mere 4.9% of the universe's total contents. Finally, the CMB has also provided scientists with an approximate, yet incredibly valuable, rate of the universe's current expansion. This expansion rate, often quantified by the Hubble constant, is estimated to be around 42 miles per hour for every megaparsec of distance. A megaparsec, for context, is a truly immense unit of distance, equivalent to about 3.26 million light-years. This means that for every 3.26 million light-years an object is from us, it appears to be receding an additional 42 miles per hour faster due to the expansion of space. Thus, the cosmic microwave background radiation, this ancient, faint glow, provides modern science with an exceptionally wide and diverse range of information, offering unparalleled insights into both the early, primordial universe and its present state. In particular, it helps us to understand the fundamental forces and components that govern its behavior, and by extension, offers tantalizing clues about what the distant future holds for it. It turns out that both the CMB itself and the various space horizons we discussed fundamentally limit what we can currently see and comprehend from our vantage point here on Earth. Let us now take an even closer, more detailed look at what these space horizons truly are, and whether, despite their apparent limitations, there might still be ways for us to peer, however indirectly, beyond them. We've already gently touched upon the concept of the cosmic particle horizon, an imaginary, ever-expanding line that forms a profound boundary for the visible universe. It sets a specific, finite distance from which light, launched into existence at some point in the deep cosmic past, has been able to travel through the expanding fabric of spacetime and finally reach an observer, right here, right now. Consequently, if other cosmic objects, such as galaxies or quasars, are situated far beyond this particular horizon, their light simply hasn't had sufficient time to traverse the immense, ever-growing distances. Therefore, we cannot, by definition, see them at this moment in time. However, it's crucial to understand that our particle horizon is not a static, unchanging barrier. It is a dynamic, evolving boundary. Over immensely long periods, as light continues its gigantic, billion-year-long paths across the cosmos, more and more of that ancient light eventually reaches us. As this occurs, the particle horizon itself slowly expands outwards, encompassing ever larger regions of space. This means that over cosmic timescales, objects that were once beyond our observable reach gradually come into view, albeit with the indispensable aid of increasingly sensitive, specialized astronomical equipment. Yet, even with this ongoing expansion of our observable sphere, we will, by the very definition of this horizon, never directly see what currently lies beyond its instantaneous boundary. It's a horizon that constantly recedes as we approach it, always keeping the truly unobservable just out of direct sight. But what if I were to tell you that there might be ingenious ways around this inherent limitation of our direct spatial inquiry? We can't directly see stars or galaxies that are, for example, 100 billion light-years away, a distance far beyond our current particle horizon. However, some extraordinarily subtle and elusive properties of our universe might just provide us with an elegant workaround, a clever cosmic bypass. Meet the neutrino, a truly tiny, incredibly tenuous, and utterly fundamental particle. Its mass, while not precisely zero, is extraordinarily close to it, making it one of the lightest known particles in the universe. But its special nature extends far beyond its minuscule mass. The neutrino has an almost unparalleled lack of interaction with ordinary matter. It's often described as a ghost particle, because it can pass through vast amounts of material, including entire planets and stars, with hardly any interaction whatsoever. This unique property means that it can safely travel over truly enormous distances, virtually unimpeded, at speeds incredibly close to the speed of light. Since neutrinos are formed as a result of many energetic and powerful cosmic phenomena, such as the nuclear fusion processes deep within the cores of stars, or the cataclysmic, explosive deaths of massive stars in supernova events, they carry precious data, a kind of cosmic message about the conditions and events of their birth. These neutrinos can journey across the cosmos to Earth, providing us with information about processes that occurred hundreds of billions of light-years away, from regions utterly beyond the reach of conventional light-based astronomy. In addition, during their incredibly long and arduous journeys, they can sometimes transform into particles with even lower energies, a phenomenon known as neutrino oscillation. It's precisely because of the almost supernatural elusiveness of neutrinos, their frustratingly weak interaction with matter, that scientists have tried, with immense dedication and ingenuity, to detect them. Neutrino observatories, often massive detectors buried deep underground or submerged in ice, are designed to catch the extremely rare instances when a neutrino does interact with an atom, producing a tiny flash of light or a subtle recoil. However, the further development of ultrasensitive detectors, pushing the boundaries of engineering and physics, will undoubtedly allow for better and more frequent detection of these ghostly messengers. And so, in the future, thanks to these tiny, unassuming particles, we may finally be able to learn what the universe is truly like beyond the cosmic horizon, unveiling secrets that light alone could never reveal. In addition to neutrinos, another remarkable cosmic phenomenon will help us explore the universe far beyond the limits of our direct visual perception. Gravitational waves. These are not waves of light or matter, but ripples, disturbances, in the very fabric of spacetime itself. They arise from the acceleration of incredibly massive objects, particularly those undergoing violent, energetic events. Think of the cataclysmic collision of two black holes, or the dramatic merger of two super, dense neutron stars, or even the rapid rotation of two massive stars around each other in a close binary system. As a result of such intensely energetic processes, these waves propagate outwards in all directions at the speed of light, carrying information about the events that generated them. When these gravitational waves pass through space, they cause a minuscule, transient stretching and squeezing of spacetime itself. While they are powerful enough to destroy less massive objects or slightly increase the distance between them in their immediate vicinity, by the time they reach Earth, having traveled billions of light years, their original power has been dramatically attenuated. They no longer pose any threat to us, and their effect on spacetime is incredibly subtle, almost imperceptible. This makes them just as difficult, if not more so, to detect than neutrinos. Yet, these incredibly faint wave remnants, these whispers from the cosmic deep, tell scientists not only what exactly happened outside our visible universe, but also at what immense distances these events occurred. For example, in 2016, scientists at the Laser Interferometer Gravitational Wave Observatory, or LIGO, a collaborative effort involving institutions like the Massachusetts Institute of Technology, made a monumental discovery. They recorded the first direct detection of gravitational waves, a signal emanating from the titanic collision of two black holes, an event that occurred an astounding 1.3 billion light-years from Earth. This groundbreaking observation opened up an entirely new window onto the universe, allowing us to hear the cosmos in a way we never could before. Gravitational waves, much like neutrinos, are our invaluable guides, our intrepid explorers, venturing beyond our limited, light-based universe. And the continuous, rapid development of technology specifically designed to capture and analyze these elusive cosmic signals is the key, the ultimate unlocking mechanism, to our future knowledge of the entire, boundless universe. However, no matter how rapidly our scientific efforts to unlock the deepest secrets of the cosmos develop, we are inherently hampered by one serious, pervasive factor, a fundamental aspect of the universe itself that we simply cannot escape. For the foreseeable future, we must, for now, largely forget about the prospect of direct visual observation of stars and galaxies located in the invisible cosmos, the regions beyond our current particle horizon. This persistent limitation is primarily due to the ongoing, relentless expansion of the universe. After the initial, incredibly rapid burst of expansion following the Big Bang, the universe's expansion did not cease. Although it did slow down considerably for a period, it has since, surprisingly, begun to accelerate again. Because of this continuous expansion, all objects in space that are not gravitationally bound to each other are perpetually moving away from each other. And this expansion isn't uniform, it becomes more rapid with distance. Specifically, for every 3.26 million light-years of separation, the rate of recession between two unbound objects effectively increases. This acceleration is believed to be under the mysterious influence of dark energy, a hypothetical force that appears to be widespread throughout outer space, acting as a kind of anti-gravity. Our particle horizon, that spherical boundary of what we can see, is not static, it is constantly expanding along with the universe itself. Therefore, the larger the universe becomes, and the more our particle horizon expands, the more objects that were previously beyond its reach gradually appear on our ever-growing star maps. It's a continuous unveiling, a slow reveal of cosmic wonders. In particular, all the stars and galaxies that we observe now, those within our current observable universe, will reassuringly never leave the boundary of our visible space. Their light will always, eventually, reach us. However, a poignant truth emerges when we look far into the distant future. The space objects currently relatively close to us, those that now populate our immediate cosmic neighborhood, and in particular, even the cosmic microwave background radiation itself, will, due to the same relentless expansion, appear as incredibly distant and significantly less bright dots in the future night sky. Their light will be stretched to an extreme degree, redshifted almost beyond detection, and their apparent size will diminish to mere points. Yet, Because of this very same expansion, many objects located far away, beyond a certain threshold, will be moving away from us so quickly that we will, paradoxically, never be able to detect the light they have emitted us from this point forward. Their light is essentially, outrunning, our ability to ever receive it. This accelerating expansion profoundly affects another critical boundary, the space event horizon. As we discussed earlier, this horizon sets an ultimate limit for any emitted signals. Beyond this boundary, none of the signals emitted now will ever reach a recipient located within our region of space, no matter how long they wait. Currently, the radius of this event horizon is estimated to be approximately 16 billion light-years. This means that even if a galaxy is presently within our particle horizon, meaning its past light has reached us, but lies beyond our event horizon, we will never be able to interact with it in the future. Any signal we might emit, for example, from Earth right now, attempting to communicate with potential extraterrestrial life in such a galaxy, would become increasingly stretched and redshifted as it travels through the expanding space. Its wavelength would grow longer and longer until it reaches frequencies that our future technology, no matter how advanced, might not be able to pick up, or it would simply be carried away faster than it could ever reach its destination. The object that emitted the signal, and the space between it and us, would be moving away from Earth at an ever-increasing rate. Therefore, we would be unable to make ourselves known to possible extraterrestrial life if it's too far away, beyond this crucial event horizon. Furthermore, a truly sobering thought emerges. In the very distant future, even the galaxies with which we are currently able to communicate, those presently within our event horizon, may eventually become unreachable to us. The expansion of the universe is relentlessly shaping the size and position of this horizon. Much earlier in cosmic history, it reached an incredible distance of about 60 billion light-years, but now, due to the accelerating expansion, it has shrunk to only 16 billion light-years. In the far, far future, this distance is projected to become even smaller. In such a scenario, we would ultimately remain isolated within our own shrinking space bubble, cut off from the possibility of future communication with distant civilizations, and severely hampered in our scientific development, as the vast majority of the cosmos would recede beyond our event horizon. Adding another metaphorical wall to this expanding, yet shrinking cosmic bubble that contains us, will be yet another crucial demarcation, the Hubble horizon. This particular limit represents a theoretical point in space, currently situated at a distance of approximately 14.5 billion light-years from us. It's a boundary of profound significance, defining the region beyond which the apparent speed of space objects, carried by the universe's expansion, begins to exceed the speed of light itself, relative to our position. To visualize this, imagine a cosmic race. The further a light-emitting object is from this theoretical Hubble horizon, the faster it appears to recede from us, not by moving through space, but because the very fabric of space between us and that object is stretching at an ever-increasing rate. For a photon, a tiny quantum of light, attempting to make its way towards Earth from beyond this boundary, it becomes an impossible struggle. The space it's traveling through is expanding away from us faster than the photon itself can move. It's a relentless, losing battle against the inexorable stretch of the cosmos. This means that only beyond this Hubble limit will the effective recession velocity of distant objects, as observed from Earth, cease to accelerate away from us at superluminal speeds. It's a point where the light can still, theoretically, catch up. However, just like its counterparts, the Hubble horizon is not a fixed, immutable barrier. It, too, is a dynamic entity, actively expanding over vast stretches of cosmic time. This ongoing expansion of the Hubble horizon implies a fascinating, albeit slow, unfolding of the universe's secrets. It means that, as aeons pass, distant light, which was once trapped beyond this limit, will gradually be able to reach our ever-improving telescopes. Therefore, in the distant future, our descendants may be able to see more and more faint traces of galaxies and stars that are currently entirely invisible to us, lying beyond our present observational capabilities. It's a slow, grand revelation of new cosmic vistas. But this relentless expansion, this endless stretching of the cosmos, brings with it not only these intriguing, slowly unfolding revelations. It also carries a profound and, in some ways, rather somber consequence for the ultimate fate of the universe we inhabit. In the unimaginably distant future, a time almost beyond comprehension, the Hubble horizon itself is predicted to undergo a dramatic transformation. It will, quite paradoxically, begin to collapse. Instead of expanding outwards, it will start to shrink, slowly but inexorably, eventually contracting around only the galaxies of our immediate cosmic neighborhood, specifically, the galaxies that make up what is known as the local group. Once this inevitable contraction occurs, a truly isolating event will transpire. After that point, no new light from other cosmic bodies, no fresh photons emitted from beyond the confines of our isolated local group, will ever again be able to reach our cosmological horizon. The light that has already traversed the vast distances and is currently on its way will eventually arrive, but after that, a deep, pervasive silence will descend. We will, quite literally, be cut off, hermetically sealed, from the entire universe beyond our immediate galactic cluster. The grand, sweeping cosmic panorama we currently enjoy will diminish, fading into a finite, localized view. But the story of these cosmic horizons doesn't end there, for an even more profound and isolating event is predicted. The space event horizon and the Hubble horizon, those two crucial boundaries that define our future observability and communicability, are projected to merge. This cosmic convergence is estimated to occur in approximately 10 billion years, a timescale that speaks to the deep, slow rhythm of universal change. When they finally unite, they will form a new, singular horizon, one with an immense radius of about 63 billion light-years. And from that point forward, once this new, encompassing boundary is established, we will irrevocably lose the ability to see or detect any events, any new light, any information whatsoever from beyond this newly formed cosmic barrier. After tens of billions of years have slowly drifted by, an epoch so vast it makes our current understanding of time feel fleeting. All light that was ever emitted beyond the limit of this merged horizon will have finally disappeared forever from our view. It will have been redshifted into oblivion, stretched beyond detectability, or simply carried away by the relentless expansion of space. The universe, as perceived from our isolated vantage point, will become a profoundly darker, emptier place, a silent, static tableau of only our local galactic neighbors. Despite the inherent, boundless curiosity that defines humanity, despite our ceaseless drive to explore and understand, the universe itself appears to have set these fundamental limits, these cosmic curtains, designed perhaps to preserve its infinite secrets, to keep some mysteries forever just out of reach. We are, in essence, surrounded by these spherical horizons, invisible yet incredibly potent barriers that, by their very nature, do not allow distant light to reach Earth. This fundamental constraint inevitably takes away our ability to fully immerse ourselves in the direct, real-time study of the grand, unfolding evolution of our universe on the largest scales. Moreover, as we've contemplated, in billions of years, these crucial horizons will merge into a singular, impenetrable barrier, effectively blocking all incoming light from beyond our local cosmic neighborhood. This convergence will completely deprive future humanity of the hope, the very possibility, of expanding its direct, observational knowledge of the truly unlimited universe that lies beyond our immediate grasp. However, amidst this seemingly bleak long-term cosmic forecast, a glimmer of hope, a testament to human ingenuity, remains. The rapid, ceaseless development of modern technology, our ever-increasing scientific prowess, promises to allow us to record more and more subtle data about deep space in the future. Thanks to the elusive neutrinos and the subtle, space-time, rippling gravitational waves, we possess alternative, non-light-based windows onto the cosmos. These messengers, unaffected by the opaque conditions of the early universe or the extreme stretching of light by expansion, will continue to bring us invaluable information from the most distant and ancient reaches of existence, and even further into the future. As our civilization potentially expands beyond Earth, we may even be able to establish new particle horizons on other planets or celestial bodies, thereby gaining new, albeit still limited, perspectives on the universe. So, while we cannot entirely get rid of these fundamental cosmic limitations, these boundaries imposed by the laws of physics, we can certainly learn to manage them, to work within their constraints, and to find ingenious ways to glean information indirectly. It will undoubtedly take many more generations, countless centuries of scientific advancement, before we can even begin to contemplate truly leaving our own, ever-expanding yet ultimately localized, horizon. But when and if we do, when our understanding and technological capabilities have grown to such an astonishing degree, there will then be an absolutely limitless number of other horizons, other cosmic perspectives that will also await our exploration, waiting to be crossed one day. All that truly remains, for now, is to patiently wait, to continue our diligent study, and to allow the majestic, slow, burning fire of scientific inquiry to illuminate our path. Since the very beginning of our species, from the first flicker of sentience in our ancient ancestors, we have been captivated by the night sky. We have consistently looked up, our gaze drawn inexorably towards that vast, shimmering expanse, and pondered, with both fear and fascination, the sheer, unimaginable vastness of the universe. We have meticulously counted the stars, those countless pinpricks of light scattered across the inky blackness. We have charted the intricate patterns of the constellations, weaving myths and stories around their celestial forms, giving meaning to the seemingly random. And, most importantly, we have dreamed, with an enduring sense of wonder, of what truly lies beyond our tiny, fragile corner of heaven, our small blue planet orbiting a single, ordinary star. But did we ever truly dare to think, with genuine seriousness, about the end? No, not merely the end of our fleeting, individual human existence, or even the eventual demise of our species, but the ultimate, profound end of time itself, the final cessation of all cosmic activity. What, in the deepest, most distant future, will the last days of the universe actually look like? What will we, or whatever sentient life remains, possibly see, hear, or even feel in those ultimate, final moments? Will everything simply go out with a cataclysmic bang, a final, furious burst of energy, or will something entirely unforeseen, something utterly beyond our current comprehension, quietly and subtly occur? Throughout the long, intricate tapestry of human history, our species has consistently thrived on the relentless exploration of the unknown, driven by an innate, almost insatiable urge to push the very boundaries of our understanding. Today, we embark on perhaps the deepest journey of all, a conceptual voyage to the very end of time. Like countless grains of sand slowly, inexorably falling within an hourglass, each passing moment brings us infinitesimally closer to the inevitable, ultimate conclusion of the universe. But the profound questions remain. How and when will this cosmic finale actually happen, and what, if anything, does it truly mean for us, these ephemeral, mortal beings, who exist for but a blink in the vastness of cosmic history? We are about to undertake a journey that crosses unimaginable scales of both space and time. We will mentally travel billions, even trillions of years, into the incredibly distant future. This is a journey not primarily of physical distance, but of time, a deliberate thought experiment undertaken for the sake of exploring the ultimate, grand fate of the cosmos. It is, in essence, a profound journey to the end of time. Here we are, in the relatively brief, yet profoundly impactful, epoch known as the Anthropocene. This is our time, our current era, a geological age uniquely defined by the colossal, unprecedented influence of our species on this beautiful, vibrant blue-green sphere we affectionately call home. We have, with astonishing speed and profound effect, shaped, manipulated, and irrevocably altered the very fabric of the Earth, its atmosphere, its oceans, and its ecosystems, all in what amounts to a mere blink of an eye in geological terms. Consider, for a moment, the Holocene, the 11,700-year era that immediately preceded the Anthropocene. It was a period of remarkable climatic stability and relatively comfortable conditions, an era in which all human civilization, in its myriad forms, was born and flourished. The Holocene truly nurtured us from our earliest days, providing the benign environmental conditions that allowed us to transition from humble hunter-gatherers, living at the mercy of nature, to the complex, technologically advanced societies we are today. It was the stable climate of the Holocene that gave birth to agriculture, enabling us to settle and cultivate land. It fostered the invention of writing, allowing knowledge to be accumulated and transmitted across generations. Indeed, it gave rise to the very notion of civilization itself, with its cities, its complex social structures, and its artistic and scientific endeavors. Nevertheless, as we, as a species, relentlessly rushed forward, driven by ambition and ingenuity, the profound and often detrimental losses inflicted upon our planet became increasingly evident. Our relentless thirst for resources, our unceasing expansion across the globe, and the sheer scale of our industrial and agricultural activities have caused fundamental changes that now clearly mark the end of the comfortable Holocene. Climate patterns, once predictable, are now shifting dramatically and erratically. Extreme weather events, once rare anomalies, are rapidly becoming the norm, increasing in both frequency and intensity. Biodiversity, the rich tapestry of life on Earth, is under unprecedented threat, with species extinction rates skyrocketing. The delicate ecological equilibrium that has sustained and nourished us for thousands of years is now teetering precariously on the brink. Our actions, our collective human footprint, have left an indelible, unmistakable mark on the very physical conditions of the Earth, unequivocally ushering in a new and profoundly different geological epoch, the Anthropocene. This is, without a doubt, a chapter of Earth's history written predominantly by human hands. As we now stand on the threshold of this new, human-defined era, a singular, critical question naturally arises: what enduring legacy, what lasting impact will we ultimately leave for the succeeding eras, for the future inhabitants of this planet, whatever form they may take? Our conceptual journey now brings us closer to the year 2500, a mere few centuries into our future, revealing some of the dynamic and potentially challenging changes the Earth would inevitably face. By this time, Earth's magnetic field, that invisible yet absolutely vital protective shield that constantly guards our planet against the harsh, energetic onslaught of solar winds and cosmic radiation, is predicted to be undergoing a belated, yet significant, shift. The north and south magnetic poles are in the slow, majestic process of reversing places, an awe-inspiring geophysical event last definitively observed approximately 70,000 to 80,000 years ago. This amazing, gradual magnetic reversal, while not an instantaneous catastrophe, is steadily disrupting our modern technology, particularly our navigation systems, communication networks, and power grids, forcing humanity to adapt in novel and unprecedented ways, devising new strategies to mitigate the effects of a weakening and shifting magnetosphere. Let us now be transported gently and quietly further into time to the year 4385. In this distant future, we are privileged to witness the magnificent return of an old, familiar friend from the depths of the solar system, Comet Hale-Bopp. This iconic celestial wanderer, first widely observed in the late 20th century, makes its majestic return to the inner solar system after its incredibly long, elliptical orbit. It would be a breathtaking sight to behold, a brilliant, luminous trail of light, a celestial beacon gracefully illuminating the night sky, serving as a vivid, humbling reminder of our small, yet significant, place within the grand, intricate dance of the cosmos. Jumping forward once more, to the year 5000, we are confronted with the grim and undeniable reality of our past actions, the long-term consequences of choices made centuries ago. By this point, the vast polar ice caps, those immense reservoirs of frozen water at Earth's extremities, will have largely melted, leading to a significant and sustained global rise in sea levels. Many coastal towns and cities, once bustling with life, vibrant centers of human activity, now lie irrevocably submerged underwater, silent relics of days long past, their structures slowly dissolving into the saline embrace of the expanded oceans. The maps of the world, as we know them today, would be profoundly redrawn. Fast forward to the year 6000, and a colossal asteroid, a truly immense chunk of primordial rock and metal, looms ominously on the horizon. Its trajectory is clear, its collision with Earth is, by this point, deemed inevitable, unavoidable. This cataclysmic impact would cause an event of unimaginable scale, a global catastrophe that would fundamentally alter life as we know it, triggering widespread environmental devastation, altering the climate, and potentially leading to a mass extinction event, forever reshaping the course of planetary evolution. By the year 8000, we are privileged to witness an extraordinary celestial event, one of immense beauty and destructive power. A distant star, having reached the very end of its long, luminous life, explodes in a spectacular, incandescent supernova. Its brilliant, momentary glow outshines entire galaxies, briefly becoming one of the most luminous objects in the visible universe. It's a poignant, yet awe-inspiring, reminder of the ever-changing, dynamic landscape of the universe, a continuous cycle of stellar birth, life, and dramatic death. The Earth and its surrounding cosmos, perpetually in motion, endlessly transforming, continually remind us of the inherent impermanence of our own journey, our fleeting existence within this grand cosmic drama. As we look out at the seemingly star-studded, yet ultimately transient, canvas of the universe, we reflect upon the immense trials and profound tribulations that lie ahead on our continuing journey to the end of time. The silent, relentless hands of the cosmic clock continue to move forward, now leaping ahead by a staggering 1 billion years. By this immensely distant future, our sun, the very source of all life, warmth, and energy on Earth, begins to undergo dramatic and profound changes. Its core, having steadily converted hydrogen into helium for billions of years, starts to alter its internal dynamics. Its luminosity, the sheer amount of light and heat it emits, increases significantly by approximately 10%. This seemingly small percentage has catastrophic consequences for Earth, scorching our home planet with an unquenchable, relentless heat. As global temperatures inexorably rise, the delicate process of photosynthesis, the very foundation of most terrestrial life, ceases entirely by around 1.1 billion years. The vibrant green carpet that once covered the Earth, the lush forests and verdant plains, begins to fade, replaced by increasingly barren, desolate landscapes, utterly devoid of macroscopic life. The atmosphere, once rich with life-giving oxygen, gradually becomes thin and depleted as the biological processes that replenish it grind to a halt. The relentless, searing heat accelerates, and by roughly 1.3 billion years, Earth's once vast, shimmering oceans, those cradles of life, begin their slow, agonizing process of evaporation. What was once a brilliant blue pearl in the cosmic expanse, a beacon of life, is gradually, inexorably, becoming a dried-up, reddish-brown, desolate wasteland. The great seas and oceans, once teeming with diverse life, turn into mere memories, their existence recorded only in the parched, cracked sediments of a long-lost past. Our long cosmic journey brings us now to the very last, ultimate chapter of Earth's history, a truly final act in the planetary drama. In the 7.5 billionth year from now, our Sun, having transformed into a bloated, incandescent red giant, will expand dramatically, its outer layers swelling far beyond its current size. In this cataclysmic expansion, it will consume our once lush, vibrant planet, engulfing Earth in its fiery, expanding embrace. This event marks the definitive, irreversible end of Earth's existence, a poetic return to the cosmic dust from which it was originally born. Our home world, which has nurtured us, sheltered us, and provided the conditions for billions of years of life, is now irrevocably returning to the raw, primordial elements of the cosmos. We fast forward again, now to the year 10 billion. After its fiery, destructive death as a red giant, our Sun will have undergone a profound metamorphosis. It is reborn, not as a vibrant star, but as a white dwarf, a weak, incredibly dense, and slowly cooling remnant of its former self. This stellar corpse is all that remains of the once raging inferno of nuclear fusion that powered our solar system. From the furious hell of its energetic past, it's now just a smoldering ember, a silent, compact spectator to the grand, ongoing cosmic drama that continues to unfold across the universe. It emits only faint, residual heat and light, a ghostly echo of its former glory. By the truly immense epoch of 100 trillion years from now, a profound and deep silence will have descended over the cosmos. The stars, those countless beacons of light that have illuminated the universe for eons, will begin to go out, one by one, like dying embers in a fading fire. Their nuclear fuel reserves, finite and exhaustible, will finally be depleted. They will leave behind an increasingly chilling, pervasive darkness, a universe in its deepest, most profound twilight. This is the era when the last of the red dwarf stars, the longest lived stars in the universe, finally wink out. By the unfathomable year of 1 quadrillion years, long after the extinction of the last stars, the overall temperature in the universe will have plummeted to an incredibly low state. Having originated in the fiery, searing origins of the Big Bang, the universe will now slowly, inexorably, sink into a profound, chilling cosmic winter. We will find the entire universe gradually slipping into an era of pervasive darkness, an epoch where the very concept of starlight becomes a distant, ancient memory. The era of starlight is over, definitively concluded. The universe, once a vibrant, sparkling tapestry, has become a vast, silent cosmic graveyard, dotted only by the ghostly remnants of what once were glorious stars. These are the last, faint remnants of the celestial bodies that once illuminated the cosmos, glowing with a faint, ghostly, residual light, a chilling reminder of the universe's fiery, luminous past. By 10 quadrillion years from now, these white dwarfs, those dense, smoldering stellar corpses, will have become the dominant celestial bodies, though their light will be so dim as to be almost imperceptible. This is the age of degeneration, an epoch where the universe is slowly winding down. It is a ghost universe, echoing with the faded memories of galaxies and stars that once shone brightly, illuminating the cosmic night. The age of extinction is a vivid, albeit stark, reminder of the endless, cyclical rhythm of birth, life, and death that permeates the universe, from the smallest particle to the grandest galaxy. But even in its last, incredibly slow gasp, the universe continues to evolve, albeit on scales and in ways that are almost beyond our current comprehension. Gravity, that fundamental sculptor of the universe, continues its relentless, unseen work. This omnipresent force, never truly resting, slowly but surely rips stars and planets from their ancient, stable orbits around their defunct stellar remnants. It hurls them, one by one, into the vast, cold cosmic void, sending them on endless, lonely journeys through the dark. These incredibly rare and slow gravitational interactions, occurring over truly immense timescales, can sometimes, paradoxically, lead to the birth of new, though short-lived, stars. Their creation, a momentary flare of light in the encroaching darkness, is heralded by ultra-bright, albeit transient, supernovas, faint echoes of the glorious, vibrant universe that once was. Meanwhile, the white dwarfs themselves, those last smoldering embers of stellar life, also begin their final, slow disappearance. Over trillions of years, they continue to cool, to shrink, and to dim. Their light, already incredibly faint, gradually fades until they disappear altogether from view, becoming utterly invisible. These dying white dwarfs are reborn, not into new stars, but into black dwarfs. A black dwarf is the theoretical final evolutionary state of a star of this type, a truly cold, dark, and utterly invisible stellar remnant, no longer emitting any significant heat or light. They mark the ultimate plunge of the universe into an era of pervasive, absolute darkness. And so, the era of black dwarfs begins, an epoch of profound cosmic stillness and cold. The universe, once a spectacular display of light and color, of dynamic energy and vibrant activity, is now a mere shadow of its former, glorious self. The journey to the end of time continues, relentlessly, into ever-deepening coldness and an all-encompassing darkness. As this vast, unfathomable amount of time continues to tick by, the universe maintains its relentless, accelerating expansion. Each region of space, every cubic light-year of cosmic fabric, stretches and thins, gradually becoming more diffuse. Space-time itself, that intricate, interwoven tapestry of reality, is pulled taut, elongating endlessly. What was once an organized, interconnected whole, a cosmic web of galaxies and clusters, now expands into something akin to a multitude of distant, isolated islands, each drifting further and further apart, lost in a boundless, ever-growing ocean of emptiness. But within this increasingly vast and desolate void, a silent, yet utterly catastrophic, event begins to occur. Protons, those fundamental building blocks of all ordinary matter, the very heart of every atom, and by extension, of all life as we know it, begin to decay. Protons, once thought to be eternally stable, those crucial constituents of atomic nuclei, slowly disintegrate into ghostly, ephemeral neutrinos and photons. Matter, the very substance of reality as we comprehend it, is, particle by particle, disintegrating, dissolving into its most basic, ephemeral components. The universe is, with an agonizing slowness, erasing the last vestiges of its physical history, its intricate material form. All that ultimately remains are fleeting particles of light and the gravitational behemoths that are black holes. At this profound point in our cosmic journey, the familiar physical phenomena that have governed the universe for eons begin to cease. We are plunged into a new, utterly alien era of cosmic history, one dominated by the most extreme objects. We are now firmly in the era of black holes. Even the seemingly eternal black dwarfs, those cold, dark remnants of stars, will have long since disappeared, having given up their residual mass to the unrelenting, all-consuming pull of the expanding universe. The very last remnants of ordinary stars, those that once shone so brightly, will have finally turned into cosmic dust, scattered and diluted across the immense void. Black holes are becoming the main, if not the only, celestial objects still dotting the increasingly dark and empty universe. In an era so utterly dominated by black holes, the remnants of once living galaxies, the supermassive black holes that reside at their cores, are of particular, chilling importance. Born from the cataclysmic deaths of massive stars and the dramatic, gravitational merging of countless smaller black holes over cosmic time, these celestial titans have grown to truly incredible, mind-boggling sizes. They have relentlessly absorbed immense quantities of matter and energy on a scale far beyond anything we could have possibly imagined in the early universe. These colossal cosmic events, particularly the mergers of supermassive black holes, emit powerful gravitational waves, causing profound ripples in the very fabric of space-time. We can think of them, in a poetic sense, as the last sounds of the universe, on the very verge of its ultimate end, a slow, deep ringing of a bell echoing faintly through the vast, cold cosmos. However, even such outstanding and seemingly eternal objects of the universe as black holes are not, as one might first think, truly immortal. The famous physicist Stephen Hawking, in the late 1970s, introduced a revolutionary concept, now widely known as Hawking radiation. This process describes how black holes, over incredibly vast timescales, slowly but inexorably lose energy and, consequently, mass. This astonishing phenomenon is a direct result of specific, subtle properties of quantum physics that operate near the black hole's event horizon, that point of no return. Here, pairs of virtual particles and antiparticles are constantly appearing and disappearing from the quantum vacuum. Occasionally, one of these particles falls into the black hole while its partner escapes into space, thereby carrying away a tiny bit of the black hole's energy. This leads to a net loss of energy and hence a gradual decrease in the mass of the black hole. Over truly enormous, almost inconceivable time scales, this slow, persistent leak of Hawking radiation causes the black hole to steadily lose mass and, as a consequence, to shrink. As this process continues, its once overwhelming gravitational pull slowly weakens, becoming less and less potent. The ultimate, inevitable result is the complete evaporation of a black hole, a process that, for even the largest supermassive black holes, would take far longer than the current age of the universe. Such events, the final disappearance of these cosmic behemoths, would mark the ultimate death of the last major objects in this universe, leaving behind a truly vast, seemingly endless cosmic void, a universe of almost complete nothingness, cold and dark. Since the Big Bang, our universe has been continuously expanding, a process driven and influenced by a special, mysterious force we call dark energy. This hypothetical form of energy is believed to permeate all of space, acting as a kind of cosmic antithesis to gravity. Unlike gravity, which pulls things together, dark energy effectively pushes things apart, causing the expansion of the universe to accelerate, not slow down. At the same time, dark matter, an equally mysterious substance that is thought to make up a staggering 85% of the total matter in the universe, creates gravitational attraction, acting as a counterbalance to this accelerated expansion, tending to pull cosmic structures together. Although dark energy currently appears to be the dominant force, driving the universe towards ever faster expansion, we must always consider the possibility of a shift in this delicate balance of cosmic forces. There are several compelling theoretical models suggesting that it is plausible that more dark matter may emerge, or its gravitational influence become more pronounced. As the universe continues its vast expansion, this slow, subtle increase in its gravitational influence could, over immense timescales, begin to outweigh the expansive force of dark energy. If the gravitational influence of dark matter were to ultimately exceed the pushing force of dark energy, the accelerated expansion of the universe could begin to slow down and quite possibly even reverse. This scenario is comparable to the effect of stretching an elastic band. The universe stretches further and further, reaching a maximum extent, before the moment of an abrupt, inevitable contraction arrives. This process, where the universe begins to pull back on itself, is often known as the Great Contraction, or more dramatically, the Big Crunch. This immense, gravitational compression would inevitably cause the entire universe to collapse in on itself, drawing all matter, energy, and spacetime back towards a central point. As the universe contracts, the density of matter and energy would increase dramatically, becoming ever more concentrated. At some point in this cataclysmic compression, we would reach a critical threshold, a moment of peak density and temperature, far exceeding even the conditions of the early Big Bang. Everything existing, every particle, every black hole, every shred of energy would be crushed into an infinitesimal point of infinite density. And in this extreme, ultimate state, the fundamental laws of space and time, as we currently understand them, would be distorted, broken, and cease to function, becoming utterly unrecognizable. It is here, in this final, singular crushing, this ultimate singularity, that another Big Bang could, theoretically, occur. Such a cataclysmic collapse could, in essence, begin the birth of an entirely new universe, a fresh cosmic cycle of continuity of existence, an endless cosmic dance of death and rebirth. This profound journey, this mental traverse through the ultimate fate of the cosmos, offers us a deep, humbling sense of our true place in the grand, sweeping timeline of the universe. We realize with quiet introspection that our existence, the entire span of human civilization, is but a brief, ephemeral moment in the colossal, almost boundless timeline of the universe. The journey to the end of time, surprisingly, brings us full circle, back to the very beginning, back to the ultimate origins of existence. And perhaps it is precisely here, in this cyclical nature of cosmic events, that we find the greatest revelation. In a universe of truly infinite possibilities, an end is not necessarily a finality, but merely another beginning, a fresh canvas for creation. More than once, you've probably caught yourself gazing into the unknown, wondering, with a sense of genuine curiosity, what will happen in the future? What will the world be like in a mere 100 years, 1,000 years, or even in the unimaginable span of 1,000,000 years? For you, for that inherent human desire to peer into tomorrow, we've attempted to look behind the veil of the future, tracing the evolution of the stars we see twinkling in the night sky every evening, all the way to the ultimate, profound oblivion that awaits the cosmos. Today, we'll try to metaphorically tame time itself, to harness its relentless flow, and to discover what our universe might look like in a mere 100 million years. A blink of an eye in cosmic terms, yet an eternity for human civilization. So, gently check your seatbelts, for in a few short, conceptual seconds, you will find yourself transported, not physically, but in mind and spirit, to the very beginning of the universe's life. From that fairy, primordial instant, we will travel all the way through its grand evolution towards its last, ultimate moments. We're about to begin this extraordinary, mind-bending journey. Of course, nothing in our universe, no matter how grand or seemingly eternal, can truly exist forever in its current form. In a mere 100 million years from now, a relatively short span on a cosmic scale, all the massive stars, those brilliant, luminous giants that currently grace our night sky and dominate the visible light of distant galaxies, will have completed their life cycles. They will have exhausted their nuclear fuel, flared brightly, and then, in spectacular supernovae, disappeared, leaving behind only the ethereal, glowing fields of nebulae, the vast interstellar clouds of gas and dust from which new stars will eventually form, or the dense remnants of neutron stars and black holes. Stars, in particular, despite appearing seemingly unchanging during their long, stable lifetimes, are in a constant state of internal evolution. They start their lives as immense, sprawling molecular clouds of gas and dust, slowly collapsing under their own gravity until their cores become hot and dense enough to ignite nuclear fusion. They then evolve over tens of millions of years, or even hundreds of millions, depending on their mass, before settling into a long period of stable hydrogen burning, shining steadily in space for millions or even billions of years. However, eventually, due to the relentless synthesis of hydrogen to form helium in their cores, their internal dynamics change. Their temperature and brightness begin to decrease, and their core gradually shrinks. This marks the beginning of their death stage, a period that, for many stars, lasts slightly less than their actual main sequence life. Then, stars with a mass comparable to our Sun will, in about 9 to 10 billion years from now, swell into enormous, luminous red giants. After billions more years in this phase, they will eventually completely fade away, shedding their outer layers to form beautiful planetary nebulae, leaving behind only dense, compact remnants in the form of white dwarfs, and a plume of gas and dust from which new generations of stars might eventually be born. However, the period of 100 million years, while short in the grand scheme of stellar evolution, will also subtly affect our own Sun. It will become noticeably brighter and warmer, increasing its luminosity by approximately 1%. While this might seem insignificant, over the vast expanse of 1 to 2 billion years, the Sun will continue to heat up to a point that becomes unequivocally fatal for life on Earth, leading to the evaporation of oceans and the eventual engulfment of our planet. But what if this inevitable, slow burning process of stellar aging could somehow be slowed down or even altered? While 100 million years is an incredibly long period for humanity, a duration that utterly dwarfs our current historical span, it is also a timescale over which our science and technology will hypothetically be able to reach a level that might seem like pure science fiction to us now. In 100 million years, humanity, or its evolved descendants, will probably have reached a point where we are able to tame the stars, to understand and influence their fundamental processes, and even to determine precisely how much longer they will shine. This incredible feat would be achieved through what we might call stellar engineering. During this vast period of time, human civilization would, hypothetically, be able to replenish the star's precious fuel reserves, perhaps by harvesting hydrogen from abundant cosmic sources and delivering it to aging stars. Or, even more profoundly, we might be able to artificially influence their intricate nuclear reactions, perhaps by carefully modulating the fusion processes within their cores. If such advanced capabilities were developed, our Sun, for instance, could conceivably survive for a significantly longer period, extending its stable, life-giving phase, and thereby not immediately threatening the continued existence of life on our planet for billions of years, longer than its natural lifespan. This manipulation of stars, this incredible mastery over cosmic processes, would also likely create entirely new conditions, fostering the development of life on planets that are not currently considered habitable. Worlds once deemed too cold or too distant from their star could be warmed, or those too hot could be modulated, opening up vast new frontiers for biological flourishing. In particular, the humanity of the far future would be able to extract vast quantities of hydrogen and helium directly from stars themselves, utilizing these primordial elements for immense energy production. As human civilization hypothetically grows to an incredible, truly galactic scale, the limited resources offered by individual planets alone would simply not be enough to supply the insatiable energy demands of such a large and widespread population. Furthermore, this fuel extraction could be achieved using theoretical mega-structures, such as the famous Dyson sphere, a colossal construct that would encircle a star, harvesting its stellar energy in close proximity. This method would not only provide an almost limitless energy supply, but also, crucially, preserve the precious resources and delicate environments on the planets where people would hypothetically live, allowing them to remain pristine and untouched. On the other hand, a fascinating, albeit darker, hypothetical scenario presents itself. What if stellar engineering, instead of extending stellar lifetimes, allowed us to accelerate their aging process, intentionally collapsing them to collect their fuel more rapidly? In such a case, life near these artificially hastened stars would become incredibly dangerous, fraught with the constant threat of stellar instability and eventual, premature demise. Moreover, the galaxies in which these engineered stars are located would begin to age rapidly, their bright, youthful glow fading much faster than natural cosmological processes would dictate. Yes, it's not only individual stars that are profoundly affected by the relentless passage of time, entire galaxies, and in particular, the one we call home, the magnificent Milky Way, also experience a long, complex life cycle. Our galaxy, along with countless others, appeared in the very early stages of the universe's formation, coalescing from vast clouds of gas and dark matter. And just like stars, galaxies are also continuously moving towards their eventual, distant oblivion. However, before they reach that ultimate state, galaxies, much like stars, will traverse a long, intricate path of evolution. One of the most significant processes in galactic evolution is merging. Over vast periods of cosmic time, smaller galaxies, drawn in by the powerful gravitational pull of larger neighbors, will slowly become part of those more massive structures. This cosmic cannibalism is a common occurrence. So, in 100 million years, the total number of small, dwarf galaxies will likely decrease significantly, having been absorbed by their larger counterparts. Concurrently, the proportion and mixture of spiral and elliptical galaxies within the universe will increase slightly, as mergers often transform spiral galaxies into more elliptical forms. The humanity of the future, with its advanced observational capabilities, will undoubtedly witness repeated examples of these dramatic galaxy mergers, especially involving small galaxies being absorbed by larger ones. These cosmic collisions can lead to the formation of spectacular new structures, such as tidal tails, those elongated streams of stars and gas ripped from the interacting galaxies, and, crucially, can fuel the growth of supermassive black holes at the centers of the newly merged galaxies. Our own Milky Way galaxy is, in fact, on a collision course with its nearest large galactic neighbor, the Andromeda Galaxy. While this might sound alarming, we truly shouldn't worry. Even in the relatively short span of millions of years, the actual collision event is not projected to take place for another 5 billion years, a comfortable distance into the future. In a mere 100 million years from now, our galaxy will have traveled approximately 978,000 light-years closer to Andromeda, a significant distance but still far from impact. However, this movement will not affect us in any noticeable way within our solar system. After the same 100 million year period, the positions of galaxies across the universe will have subtly changed. They will have drifted, ever so slightly, moving into regions with different densities of matter and different gravitational environments. These subtle shifts will affect their morphology, their overall shape and structure, and their rates of star formation in diverse and intriguing ways, depending on the local cosmic conditions. But in the incredibly distant future, even these bright, beautiful, and dynamic galaxies, those grand cosmic cities of stars, will eventually fade away. The primary reason for this ultimate dimming is the inevitable death of their constituent stars, especially the massive, short-lived ones, which are the primary determinants of a galaxy's overall color and brightness. After the last spectacular explosion of a massive star, a supernova that briefly outshines its entire galaxy, most of its gas and dust will remain gravitationally bound within the galaxy, continuing to fuel new star formation, albeit at a reduced rate, thereby keeping the galaxy alive, though less vibrant. However, some of this precious interstellar gas and dust will inevitably be ejected from the galaxy, perhaps by powerful stellar winds or supernova shockwaves, escaping into the vast intergalactic void. Because of this gradual loss of raw material, fewer and fewer large, bright stars will be formed over time. The overall mass of the galaxy will slowly suffer, diminishing over eons. And in billions of years, for many galaxies, it's quite probable that only a massive, central black hole will remain in its place, surrounded by a diffuse halo of old, dim, red dwarf stars and stellar remnants, a ghostly echo of its former glory. In fact, it is practically impossible to find anything truly static, anything utterly unchanging in our universe. Absolutely everything is in a constant state of motion, of flux, of transformation. And this includes, perhaps most profoundly, the universe itself. From its very inception, the cataclysmic event we call the Big Bang, the universe has never stopped expanding. In the earliest stages of its existence, during what's known as the hot Big Bang phase, the universe expanded at an incredibly rapid, almost unimaginable rate, faster than the speed of light itself, a phenomenon known as cosmic inflation. Only after this initial period of hyper-expansion, when the universe began to cool down and the energy density of matter became higher than that of radiation, allowing for the formation of fundamental particles like protons, neutrons, and electrons, did the speed of expansion slow down a bit. And over the course of the next 5 billion years, this expansion continued to slow considerably. However, both now and in the foreseeable future, the universe will not cease its expansion. It's crucial to understand that this expansion does not mean that matter is physically moving through space at high velocities. Rather, it means that space itself, the very fabric of space-time, is expanding, stretching, and growing. Imagine it like a balloon with two dots drawn on its surface. As you inflate the balloon, the dots don't move across the surface, but the surface itself stretches, carrying the dots further and further apart. The more you inflate it, the greater the distance between the dots. However, this cosmic expansion hardly affects objects that are gravitationally bound together, such as our own Milky Way galaxy and its neighbor, Andromeda, which are drawing closer due to their mutual gravitational attraction. Nor does it affect even smaller, more tightly bound systems like our solar system or even ourselves. Within these gravitationally bound structures, local forces are much stronger than the expansion of space. The total amount of ordinary matter and dark matter always remains constant within the universe. Only the effective density of matter changes due to its spread over an ever larger volume of expanding space. Nevertheless, we can clearly observe that other galaxies, those not gravitationally bound to our local group, are indeed moving away from us, their light redshifted as space expands between us. In 100 million years, the galaxies of our local group will have drifted further apart. Distant clusters of galaxies, like CLJ 11-120, which is already incredibly far, will probably become almost imperceptible, their light stretched and dimmed beyond easy detection. However, the expansion of the universe is not only ongoing but is, in fact, accelerating. The current rate of this accelerated expansion is approximately 44 miles per hour for every megaparsec, which means that for every 3.26 million light-years of distance, the speed at which galaxies recede from each other increases by that amount. This accelerating expansion will not end well for the long-term future of the universe. In millions of years, it would become progressively harder for new cosmic bodies, such as stars and galaxies, to form. The fundamental building blocks of matter, the vast clouds of gas and dust, would be dispersed too quickly by the expanding space, preventing them from collapsing under gravity to form new structures. The main factor driving this accelerating expansion, and thus this dire future, is the mysterious dark energy. Because, hypothetically, dark energy can directly counteract the gravitational attraction of matter, it acts as a pervasive, repulsive force. Dark energy is a hypothetical form of energy and a necessary property of spacetime that can lead to inevitable and profound consequences in the far future. So, in 100 million years, the expansion rate may increase so significantly that galaxies would effectively stop merging and thus cease to evolve in the ways we currently understand. The mass of dust and gas that is ejected after the death of stars, instead of remaining within the galaxy to form new stars, would be dispersed into the vast, expanding intergalactic void, becoming too diffuse to coalesce. New stars would form less and less often, eventually ceasing altogether. Moreover, in billions of years, this leakage of gas and dust from galaxies may become too fast, too efficient. In such an extreme case, absolutely nothing new will be able to form: no new stars, no new galaxies, and certainly no new life. The universe would effectively run out of the raw materials for creation. This scenario ultimately leads to what is known as the heat death of the universe. The heat death, it's important to clarify, is not related to the transformation of our universe into some kind of fiery hell through the evolution of stars. Instead, this scenario for the future fate of the universe is based upon the fundamental principles of the second law of thermodynamics. According to this law, in any closed system, entropy, which is essentially the measure of disorder or randomness, always increases over time. This means that energy will inexorably dissipate and spread out in such a way that absolutely nothing will be able to form into something unified, something organized, or something useful. You can think of it as the heat energy slowly leaving your hot cup of tea and dissipating into the surrounding room. Eventually, the temperature of the tea becomes precisely the same as the room, a state of thermal equilibrium. At that point, you can no longer extract warmth from the tea. When you drink it, the drink is no longer doing its intended job of warming you. Similarly, in the context of the universe, galaxies will become so incredibly far apart that they are essentially isolated islands in an ocean of ever-expanding emptiness. Stars will eventually start to fade and die because there will be no more necessary inflow of energy or matter from their surroundings to fuel their evolution, or to form new planets or other space objects around them. The universe, in this incredibly distant future, will become completely dark, profoundly cold, and utterly empty, a vast, featureless expanse of diluted particles and dying black holes. Dark energy, that mysterious accelerating force, may threaten not only the heat death in the distant future. If its expansive influence becomes many times faster, much more potent, over the next 100 million years, then the universe can expect an even more absolute and violent end. In this future scenario, stars will not just stop forming as in the previous heat-death scenario. Nothing will ultimately exist, not even fundamental particles. Since matters such as stars remain gravitationally bound and do not increase their mass through expansion, they might remain intact for a time. But when, in a few billion years, the expansion can become immeasurably fast, the very fabric of space itself stretching at incredible rates, the stars will not be able to withstand such an influx of expansive energy. They will simply be torn apart, their internal forces unable to resist the overwhelming outward pull of dark energy, leading to a more violent, complete destruction. Another, even more cataclysmic, scenario for the ultimate end of our existence is known as the Big Rip. This theory suggests that since the acceleration of expansion, driven by dark energy, probably cannot be influenced or stopped in approximately 200 billion years, it will become so incredibly fast and powerful that gravitational interactions will be completely broken. Planets will be ripped from their orbits around stars. Subsequently, the electromagnetic force, which maintains the integrity of stars and planets, will no longer be able to resist the overwhelming, outward force of dark energy, and these celestial bodies will be torn apart. Given even more time, an unthinkable duration, even the strong nuclear force, which holds atomic nuclei together, will not be able to resist, and atoms themselves will be ripped apart into their constituent quarks and leptons. Moreover, there's a possibility that after the Big Rip, everything in the universe will return, not to a primordial hot plasma, but to a state akin to the first stages of the Big Bang, but in a profoundly different form. However, what will remain in this final singularity, if it even forms, will not look like the incredibly hot, dense plasma that characterized the beginning of the Big Bang itself. Instead, it will be cold and extremely dilute, the exact opposite of the fiery, dense conditions of creation. This suggests that no matter how terrible or absolute the hypothetical end of the universe may be, there is always a chance, however faint, that this end will simply be a new beginning, a fresh canvas for another cosmic cycle, another potential danger to the entire universe, a threat of a fundamentally different nature, may be hidden, ironically, within ourselves, within the very fabric of matter that constitutes our being. We all know that everything around us, from the smallest dust mote to the grandest galaxy, is ultimately made of atoms. At the core of every atom lies its nucleus, typically composed of two elementary particles, the proton and the neutron. We also currently understand that these particles are incredibly stable within the nucleus, meaning they cannot, under normal circumstances, spontaneously decay into lighter particles. But what if this isn't necessarily true for all time? What if their stability is not absolute, but merely incredibly long-lived? The proton, in particular, is one of the most common and fundamental particles in the universe. It can exist even outside the nucleus, as a free proton. The proton, as we understand it, has several profound reasons to be stable, namely the fundamental laws of conservation of energy, electric charge, and baryon number. According to the current standard model of particle physics, the proton cannot decay in any way. It is considered an absolutely stable particle. However, the latest theoretical frameworks, such as the theory of grand unification, GUTIS, which attempts to combine the three fundamental forces, electromagnetism, the weak nuclear interaction, and the strong nuclear interaction into a single, overarching force, allow for the possibility of proton decay. So, in the incredibly distant future, there is a theoretical, albeit unproven, possibility that this fundamental particle will indeed decay. This seemingly unlikely process, if it occurs, is not immediately likely to cause a catastrophic disaster to the entire universe on an instantaneous scale. However, if proton decay were to happen on a massive, pervasive scale, then over millions, or even billions of years, a significant portion of the universe, the very matter that makes it up, would simply cease to exist in its current form. Proton decay would relentlessly destabilize the nuclei of atoms, causing them to break apart and produce various decay products, such as positrons and neutral pions. This fundamental disintegration of matter could profoundly affect the entire structure of the universe as matter itself slowly begins to unravel. Yet, the entire world, the entire cosmos, would not necessarily disappear all at once. Instead, the entire system of galactic evolution, the intricate processes of star and galaxy formation, in the specific regions where proton decay occurred, would be severely disrupted and ultimately cease. The people of the far future, if they still exist, can perhaps exhale a sigh of relief. The protons in their own bodies are highly unlikely to decay within any biologically relevant timescale. However, the 100 million year time frame we are currently contemplating may bring another, more immediate threat, in addition to the long-term scenarios of heat death and the Big Rip. If the collapse of protons, or rather, the instability that leads to their decay, were to become too large and too strong, it could hypothetically trigger an inevitable, even more terrible scenario for the end of the universe. but not due to protons alone. The complete destruction of all matter in the universe, without even a hint of its former existence, is hypothetically possible through a phenomenon often described as a bubble of true vacuum. You've probably heard of the Higgs boson, that fundamental particle, often called the God particle, which is a fundamental component of the Higgs field. This theoretical field permeates the entire universe, and it is through interactions with this field that other elementary particles acquire their mass. In addition, the Higgs field can profoundly affect the very nature of the vacuum itself. We are used to thinking that a vacuum is simply empty space, a void. However, in the quantum world, a vacuum is far from empty, it is teeming with quantum fields. So, a vacuum simply contains as little energy as possible, its lowest energy state. The Higgs field specifically determines whether the universe is currently in a true vacuum or a false vacuum state. A true vacuum implies that the universe is in its most stable, lowest possible vacuum energy state, like a ball resting at the very bottom of a valley. A false vacuum, on the other hand, means the universe is metastable, existing in a higher energy but less stable state, like a ball resting in a shallow dip on a hillside, poised to roll into a deeper valley if given a sufficient push. According to modern theoretical data, our universe is currently believed to be in a metastable, or false vacuum, state. This is precisely the profound, existential threat to all future life and matter. If, in 100 million years or at any point in the future, an event occurs in the universe that possesses an enormous amount of energy, such as an incredibly massive proton decay event, or perhaps the collision of two ultra-heavy black holes, then a small particle of the universe, a tiny region of space, could hypothetically be able to tunnel into a state of true vacuum. This would be a quantum event, a sudden phase transition. Once this occurs, a bubble of true vacuum would form, a tiny region of lower energy. This bubble, once initiated, would then expand outwards at an incredible speed, at almost the speed of light, relentlessly destroying all matter and fundamental particles in its path. As this bubble of nothingness expands, it would convert the higher energy false vacuum into the lower energy true vacuum, obliterating everything it encounters. Life, in any form we can conceive, could hardly appear or persist after such an intervention. The fundamental constants of physics within the true vacuum might be entirely different, rendering all known matter unstable. The universe, as we know it, its very laws and composition, would fundamentally change over time, and one day become completely unknown to us, utterly alien. It would continue to evolve, but like all of us, all things, it will eventually begin to fade away. At what precise point this will happen, we simply don't know. No matter how hard we strive to look into the future, to predict its exact unfolding, we will never get an absolutely accurate prediction. The universe is too complex, too vast, and its fundamental processes too subtle. However, one thing we can say for sure about the future is that humanity, or its incredibly advanced descendants, will undoubtedly witness more than one outstanding, groundbreaking discovery. These future revelations, perhaps in 100 million years or far beyond, will hopefully unravel the full, intricate history of the universe, and indeed, of ourselves, for the humanity of the future. Space, that truly final frontier, is not merely empty blackness, it is a mesmerizing cosmic tapestry, an intricate weave of countless stars, swirling galaxies, and ethereal nebulae, all stitched together by the invisible, powerful threads of the universe itself. But what happens when we stumble upon a breach in this grand, seemingly perfect cosmic design? A place where the cosmic loom appears to have abruptly jerked, leaving behind an almost unfathomable immensity of nothing. Imagine, if you can, an area of space so truly vast and so utterly empty that if you were to travel at the very speed of light, It would take you more than 330 million years to traverse it from one side to the other. That's a distance approximately 23 times larger than the entire diameter of our own magnificent Milky Way galaxy. It's a region so profoundly barren, so starkly devoid of celestial inhabitants, where the average density of galaxies is so strikingly low, that it fundamentally challenges our deepest understanding of cosmic structure and how the universe ought to be organized. This is not the stuff of science fiction, not a fantastical creation of an imaginative mind, but a very real, very mysterious feature of our actual universe. Welcome, my friends, to the Great Void, a cosmic mystery, an abyss of darkness, an expanse of profound emptiness that continues to baffle our understanding of the universe and its very formation. To truly appreciate the immense significance of our conceptual cosmic journey into the heart of the void, we must first gently travel back in time, back to an era when the very concept of cosmic voids was just a faint, fleeting glimpse in the eyes of the earliest astronomers. Towards the end of the 18th century, a new and exciting era of astronomy dawned, largely propelled by the revolutionary invention and refinement of the optical telescope. With these powerful new instruments, astronomers began to meticulously map the cosmos with unprecedented accuracy and detail. Yet, as they charted the shimmering expanse of our own Milky Way galaxy, they could hardly have imagined the truly vast, intricate cosmic structures that lay far beyond their immediate field of view, utterly hidden from their early instruments. Let us now fast forward to the 20th century, a period that witnessed the true advent of modern telescopes and highly sophisticated observational techniques. These technological leaps opened up the universe to our gaze like never before, allowing us to peer further and with greater clarity into the cosmic depths. Astronomers, with growing astonishment, began to realize that our Milky Way was not an isolated, singular entity, but merely one of billions of galaxies, scattered across an unimaginably vast and complex universe. As they meticulously plotted the distribution of these countless galaxies across the observable cosmos, they began to notice something profoundly strange, a subtle yet persistent anomaly. In some immense areas, there were significantly fewer galaxies than expected, vast regions that appeared almost barren. These seemingly empty areas, initially thought to be mere observational anomalies or perhaps simply regions of sparse distribution, later became definitively known as cosmic voids. It was only in the second half of the 20th century that the concept of cosmic voids truly began to gain significant momentum and scientific acceptance. In the 1970s and 80s, groundbreaking studies utilizing redshift surveys, a crucial method employed to measure the distance to galaxies by analyzing how their light is stretched by the expansion of the universe, began to reveal the large-scale structure of the universe with astonishing clarity. These surveys demonstrated, unequivocally, that galaxies were not scattered randomly or uniformly throughout space. Instead, they appeared to form a kind of intricate, interconnected cosmic web, a vast network of filaments and clusters, with immense, sweeping expanses of void, those regions of relative emptiness, stretching between them. These voids, therefore, were not just the absence of galaxies, but integral, fundamental parts of the cosmic fabric, defining the boundaries of the great galactic superclusters. With the subsequent advent of advanced digital technology and the deployment of even more powerful, sensitive telescopes in the late 20th and early 21st centuries, our understanding of these mysterious voids has expanded dramatically. Groundbreaking projects like the Sloan Digital Sky Survey, SDSS, and the 2DF Galaxy Redshift Survey, 2DF-GRS, have produced incredibly detailed, three-dimensional maps of the universe, meticulously charting the positions of millions of galaxies. These comprehensive surveys have unveiled the cosmic voids in their full, awe-inspiring entirety, revealing their immense scale and intricate distribution. The discovery and subsequent exploration of cosmic voids, from the earliest, tentative hints gleaned by astronomers to today's highly advanced instruments and sophisticated methods, represents a truly fascinating and ongoing chapter in our relentless quest to understand the universe. Yet, despite all our remarkable progress, these vast, echoing realms of apparent nothingness continue to baffle and intrigue scientists, pushing the boundaries of our cosmological models. Among these many cosmic voids, the Great Void stands out as a separate, even more profound mystery. It's a void so immense, so starkly empty, that it demands special attention. As we delve deeper into its profound mysteries, we can't help but wonder, with genuine scientific curiosity, how, precisely, did such an astonishingly large and empty structure come to be? What fundamental processes, what cosmic forces, were at play in the early universe to carve out such an immense, barren expanse? As astronomers continued to observe the universe with ever-increasing precision and depth, they began to uncover an intriguing, consistent pattern in the large-scale distribution of galaxies. Let's start with the fundamental observation that, on a truly large cosmic scale, galaxies are decidedly not scattered randomly or uniformly throughout the universe like dust motes in an empty room. Rather, they tend to cluster together, gravitationally bound, forming complex, interconnected networks of cosmic structures. These vast networks are often referred to as the cosmic web, a truly apt metaphor. This web consists of dense clusters of galaxies, where thousands of galaxies are gravitationally bound together. These clusters are then interconnected by long, thin filaments or threads of galaxies stretching across millions of light years. And between these dense clusters and connecting filaments lie the vast, sprawling empty spaces, the voids. These voids, therefore, look like immense regions of space characterized by a significantly smaller number of galaxies, a stark and profound contrast to the densely populated clusters and the intricate threads of the cosmic web. The realization of this large-scale structure of the universe was a monumental milestone in our understanding of cosmic voids. It made it clear that these voids were not simply the result of insufficient observations or random fluctuations in galactic distribution. Instead, they were integral, fundamental parts of the cosmic fabric itself, as important to the overall architecture of the universe as the galaxies and clusters themselves. They define the large-scale geometry and distribution of matter. Now that we've traversed the conceptual cosmic maze that led to the discovery and recognition of voids, let us delve into one of the most mysterious and largest voids confirmed to date, a void so immense, so astonishingly empty, that it has rightly earned the impressive nickname, the Great Void. Welcome, my friends, to the Bootes Void, named after the constellation Bootes, the herdsman in which it is primarily located. This colossal void, first discovered by the intrepid astronomer Robert Kirshner and his dedicated team in 1981, is without a doubt one of the very largest known voids in the entire observable universe. Just how truly big is it? For comparison, consider this. The estimated diameter of this astonishing void is approximately 330 million light-years. To put that into perspective, if you were somehow able to travel at the unfathomable speed of light, it would take you a mind-boggling 330 million years just to cross it from one side to the other. That's not a round trip, just one way. This makes the Bootes Void about 23 times the size of our own magnificent Milky Way galaxy, which itself spans about 100,000 light-years. The Bootes Void is not only incredibly large but also astonishingly empty. In an area of space where, according to our cosmological models, we would normally expect to find at least 10,000 galaxies, there are, incredibly, only about 60 galaxies that have been identified within the vast expanse of the Bootes Void. Think of it as a truly cosmic desert, an immense, echoing expanse of profound emptiness, almost devoid of matter, existing amidst a densely populated cosmos teeming with countless galaxies. The very presence of such a colossal, starkly empty void, with its extreme density of galaxies, initially seemed to contradict the cosmological principle, which, on a large enough scale, posits that the universe should appear roughly the same in all directions, both homogeneous and isotropic. The Beau-Tesse void challenged this fundamental assumption. The mysteries of the Beau-Tesse void are not limited solely to its immense size and its profound emptiness. For example, some of the few galaxies that do inhabit this void are bizarrely arranged, not randomly, but in a peculiar tubular structure, almost like a faint, ghostly string of pearls stretched across the emptiness. The precise reason for this unusual arrangement, this distinctive morphology, is not yet fully explained by our current cosmological models, adding another layer of intrigue to this already enigmatic region. As we continue our journey through the cosmic seas of emptiness, our next stop brings us to yet another prominent void, one that has earned the truly impressive and fitting name, supervoid. This is the Eridanus supervoid, sometimes referred to as the cold spot. The Eridanus supervoid, named after the constellation Eridanus, the river in which it is observed, is not merely a void, it is a supervoid, an exceptionally large and underdense region of space. It's considered one of the largest single structures ever definitively discovered in the universe. Just to give you a further idea of its truly staggering scale, this supervoid extends approximately 1 billion light-years across. If you were traveling at the speed of light, it would take you a staggering 1 billion years to cross it from one side to the other. This makes it many times larger than the Beau-Tesse void. The Eridanus supervoid is not only absolutely huge, but also incredibly barren. While it may not be quite as utterly devoid of galaxies as the Beau-Tesse void, its vast space is still strikingly empty and underpopulated compared to the galaxy-rich cosmos that surrounds it. It's a truly immense patch of cosmic emptiness, a profound dip in the otherwise intricate cosmic web. But what makes the Eridanus supervoid particularly intriguing, even beyond its sheer size or its profound emptiness, is its proposed connection to a mysterious cosmic phenomenon known as the cold spot of relic radiation. The cold spot of relic radiation is an unusually large and significantly colder region observed in the cosmic microwave background, CMB, that ancient afterglow of the Big Bang we discussed earlier. This particular patch of the CMB is about 70 microkelvin colder than the average temperature of the background radiation, a significant anomaly. Some scientists actively speculate that this enigmatic cold spot could indeed be the result of the immense Eridanus supervoid. The theory is that as photons from the CMB passed through this colossal void on their journey to Earth, they would have experienced a phenomenon known as the integrated Sachs-Wolf effect. In this effect, photons lose a tiny amount of energy as they climb out of the shallower gravitational potential well of the void, resulting in a slightly colder patch of relic radiation being observed. If this theory is correct, it provides a powerful link between the vast, large-scale structures of the universe and the subtle, primordial fluctuations in the CMB. As we continue our expansive journey through the cosmic deserts of emptiness, we encounter yet another mysterious expanse of nothingness, another testament to the universe's incredible scale. Welcome now to the KBC's Kardashev-Berezin-Chernin supervoid, often referred to as the Canes Venatici supervoid, named after the constellation Canes Venatici, the hunting dogs, in which it is observed. This supervoid, like its colossal counterparts, is a compelling illustration of the sheer scale and profound vastness of our universe, a truly immense region of space with significantly fewer galaxies than expected by our standard cosmological models. To truly grasp the immense scale of this particular supervoid, Consider this: it boasts an incredible diameter of approximately 1.2 billion light-years. That's about 8 times the size of our Milky Way galaxy, and even larger than the Eridanus supervoid. Traveling at the speed of light, it would take you more than 1 billion years to traverse it from one end to the other. Like a cosmic desert stretching out endlessly among the lush, galaxy-rich forests of the cosmic web, the Canes Venatici supervoid is an area of deep, profound emptiness, a vast, underdense expanse. While the sheer size and profound emptiness of the Canes Venatici supervoid are undeniably fascinating, the crucial question that continues to puzzle cosmologists remains: how did such a massive void truly form? What fundamental processes in the very early universe, what interplay of forces could have possibly led to the creation of such a vast, sprawling expanse of emptiness, so utterly devoid of the usual cosmic structures? Although the exact, precise processes that led to the formation of these immense cosmic voids are still largely unresolved, remaining subjects of active research and debate, several convincing and intriguing theories have been proposed to explain their origin. The first potential scenario involves the profound concept of cosmic inflation. It is widely believed that shortly after the Big Bang, in a mere fraction of a second, the universe underwent an incredibly rapid, exponential expansion, a phenomenon known as inflation, which literally stretched space itself to unimaginable scales. During this incredibly brief but immensely powerful inflationary period, tiny quantum fluctuations, microscopic variations in energy density that are inherent to quantum mechanics, may have been stretched and intensified on a cosmic scale. These amplified quantum fluctuations would have led to slight, but significant, differences in the density of matter and energy across the nascent universe, creating both denser regions and less dense regions of space. Over billions of years, under the relentless pull of gravity, matter would have naturally gravitated towards these denser regions, slowly clumping together to form the intricate networks of galactic clusters and filaments we observe today. This process would, conversely, have left behind the less dense regions, which then expanded further to become the vast, echoing cosmic voids we now study. The second compelling theory concerning void formation has to do with dark energy, that mysterious, pervasive force that we believe is currently causing the universe's expansion to accelerate. Dark energy may have played a crucial, active role in the formation and growth of these voids. By exerting a repulsive force, dark energy could have effectively pushed galaxies away from less dense regions, actively inflating these voids over cosmic time scales. As dark energy became dominant, it would have exacerbated the initial density differences, further emptying out the already underdense regions. Finally, the formation of cosmic voids may also be intrinsically related to the large-scale structural processes that govern the universe's evolution. As matter in the universe, primarily in the form of dark matter and ordinary gas, gradually clumped together under its own gravitational pull, forming structures such as individual galaxies and then larger galaxy clusters, voids naturally formed in the remaining, increasingly empty spaces between these growing structures. This process is strikingly similar to the formation of bubbles within a loaf of bread as it rises and bakes. Just as the dough forms solid, interconnected structures around the air pockets, the universe forms intricate structures of matter, the cosmic web, around these vast spaces of emptiness, the cosmic voids. These are just some of the leading theories that scientists are actively exploring and refining to explain the formation of these enigmatic cosmic anomalies. But as vast, as mysterious, and as profoundly empty as these great voids appear to be, they are, in fact, just one intricate piece of a much larger, incredibly complex cosmic puzzle that scientists are still diligently trying to piece together. The exact, precise processes that ultimately lead to the formation and evolution of these voids are still largely shrouded in mystery, and fully uncovering them remains a daunting and incredibly challenging task for modern cosmology. One of the main problems and inherent difficulties lies in the sheer scale and profound complexity of the universe itself. The universe is unbelievably vast, spanning billions of light years, and it is filled with countless galaxies, each possessing its own unique properties, its own intricate internal dynamics, and its own unique evolutionary history. Understanding how these countless galaxies interact with each other, how their gravitational dance influences the distribution of matter, and how they ultimately affect the larger, grander cosmic structure is a truly Herculean task, demanding immense computational power and sophisticated theoretical models. Another significant difficulty stems from the elusive, almost ghost-like nature of dark matter and dark energy. These invisible, yet immensely powerful, forces are thought to play a truly crucial and dominant role in shaping the large-scale cosmic structures we observe, including the formation and evolution of the voids themselves. Yet, our current understanding of what dark matter and dark energy actually are, of their fundamental properties and interactions, is still in its infancy. We know their effects, but not their essence. Without a clearer, more comprehensive understanding of these enigmatic components, fully comprehending their precise influence on void formation remains a considerable and persistent challenge. Despite these formidable obstacles, current research in this fascinating field is incredibly dynamic, vibrant, and constantly evolving. Scientists around the world are utilizing increasingly sophisticated tools and cutting-edge techniques to explore the mysteries of the great voids. These range from advanced, next-generation telescopes capable of peering deeper into the cosmic past to incredibly sophisticated computer simulations that can model the evolution of the universe from the Big Bang to the present day. Large-scale sky surveys, such as the aforementioned Sloan Digital Sky Survey, continue to meticulously map the three-dimensional distribution of millions of galaxies throughout the universe, providing invaluable, rich datasets for the detailed study of cosmic voids. Meanwhile, complex computer simulations, running on supercomputers, allow us to recreate the evolution of the universe under different initial conditions and varying cosmological parameters. This helps in rigorously testing different theories of void formation and understanding how various factors contribute to their emergence. In this relentless quest to understand the origin and nature of these vast cosmic voids, each new discovery, each subtle piece of observational data, each refinement of a theoretical model, brings us one crucial step closer to unlocking the profound truth behind these immense empty spaces. The great voids, far from being mere regions of nothingness, actually have profound implications for cosmology and our fundamental understanding of the universe and its grand structure. First and foremost, they present a unique and invaluable perspective on the critical role played by dark matter and dark energy, those two elusive yet utterly dominant components of our universe.